Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. You'll get notifications for this series, Linear Algebra 1, and a bunch of others on our channel. We're in Chapter 1, which is Systems of Linear Equations. 1.4, we're going to do a recap, which is 2 equations and 2 unknowns, essentially. And then what I'm going to point out also in this lecture, I'm going to use it to give an overview of the 3 cases for solutions. 1 solution, no solution, infinitely many solutions. Yeah, I'm going to keep saying it through the whole course. And we're going to do that couched inside the solutions to 2x2 linear systems. Lines in the plane and their intersections give us a nice geometric interpretation to the 3 cases of solutions in all cases. Let's do that. Alright, for 2 equations and 2 unknowns, basically what we're going to do is I'm going to recap what we did last time, and I'm going to squeeze in a little bit more terminology along the way, because the next section we're specifically going to get a bunch of terminology and systematically find out that there's only ever one solution, infinitely many solutions, or no solutions, and it won't matter the size or the number of variables or the number of equations, which is good. That's the first thing you cling to in the ocean of mathematical chaos, is the fact that there's only 3 kinds of solutions, and you're looking for them, and then we're going to train you how to get those 3 kinds of solutions, and then we're in business, wizards. The first case is going to be what we're really doing is we want to manipulate, and I'm showing you in a 2x2 system if I know what I'm doing. It's the last row essentially that I want to focus on eventually. So this is why it's good to start off with 2x2 pedagogically, to show you there's only ever 3 cases. If now I have 2 equations in the plane, what we're doing geometrically, which is hard at first because there's so much going on, but in the geometric avatar that is the associated algebraic avatar that we're giving you, the geometric avatar that you always forget to picture is saying that this is a y equals mx plus b equation. If you move the y over and the 3 over, that's y equals x minus 3. So these are lines in the plane that you've been trained, hopefully, to recognize. We write them in a different form because we want to solve linear systems, but what we're asking is find all points x, y in the plane that are on both of these lines, that are on both of these lines, or that are on both of these lines. And there can only be 3 cases. They can be distinct lines which are not parallel, and therefore they have one unique intersection point. And how do I do that? I can start manipulating the equations, which is what we're going to do, so I do it here. What we really do is you're allowed to replace any equation with that equation added to a multiple of another equation. That's the weird one. What? So what I'm going to do is just do equation 2 minus equation 1. X minus x is 0. Negative y minus y is negative 2y's. And 3 minus 4 is negative 1. Why have we done that? It's going to be called elimination because we've now eliminated variable x from the scenario, and now I have 1 equation and 1 unknown. I can quickly solve for y, and then I back substitute and use the other equation to find what x is, and I have my unique solution. Done. In this other scenario now, it's not changing. The strategy will be the same because I know I'm trying to funnel down and only ever have a unique solution, infinitely many, or none. This time, again, what I'm going to do is I start noticing, and with 2x2 systems, you'll eventually be able to start noticing this equation looks like it's just 2 times this equation. How do we rigorously check that out? Now I'm going to do equation 2 replaced by equation 2 minus 2 times equation 1. 2x minus 2x is 0. 2y minus 2y is 0. And 8 minus 2 times 4 is 0. Therefore, I just get a tautology, 0 equals 0. And what that secretly means is, because we're always solving for the last one, that's 0 times y equals 0. And if you look at one of our first videos, and when we do the cases of 1 equation and 1 unknown, that means that y is free to be anything. It doesn't matter. That's a tautologically true statement, which is always true. Therefore, y could be anything to be free, any real number, and we have infinitely many solutions. And again, we backtrack up and use the last equation to say that x is 4 minus y. And then we have the general solution, or the best one is you don't have to write anything. The general solution is the empty set when there's no solution. If I have this, I'm going to do the same move again. I'm going to focus on the last equation, and I'm going to subtract the last equation from the first equation. This time what I get is x minus x is 0. Y minus y is 0, but then 3 minus 4 is negative 1. And I don't want 0 to equal negative 1. That says our system has a solution if and only if 0 equals negative 1, which is bad. Therefore, there's no solution to this linear system. Please subscribe right here, hit the notification bell. I'll see you next time for general solutions to m by n linear systems.